Greetings everyone, this is Mr. Muller. In this video I'm going to go through example problem 11 so that you can see a problem like this. This is a great problem to review for the quiz on Monday. So when I look at example problem number 11, I'm noticing that there's three blocks. They're connected with lightweight, essentially massless strings, and they're hung over pulleys at opposite ends of the table as shown in the diagram. The table is frictionless, okay, so there's not going to be any friction acting on this center block. Friction is just an anti-sliding force. So that's not present here. It's asking how fast does the 9 kilogram block accelerate when released from rest. So if the 9 kilogram block is accelerating, but it's attached to all these other blocks, that means that this whole system is going to be accelerating. And so in order to figure out the acceleration, I'm going to need to use Newton's second law. The net force on the system is equal to mass times acceleration. But I need to use this for the whole system. So we need to figure out what the net force is, and we're going to do help minus hinder. But there's all these different objects and all these different forces acting. So let's try to apply Newton's third law to see if some of these can't cancel. First off, I'm going to go ahead and define the direction of the acceleration. Okay, and so the acceleration is going to be going in the direction of the 9 kilogram block, because that is much more massive than the 2 kilogram. And so if we wanted to, we could really imagine that these three blocks were actually in a line accelerating in one direction, and we would solve the problem exactly the same way. The pulley just changes that direction, but even though it kind of looks funky, we can actually treat it as if they were all in a line. So the next thing we need to do is we need to look at which forces are acting. So there's definitely a force of gravity, okay, on that 9 kilogram rock and by the earth. And then there is a force of gravity on this little guy over here, on the 2 kilogram block by the earth. And so we've got these two forces. You'll notice the earth's pulling more on the more massive block. And then also there's a force of gravity on the center block as well. Force of gravity on the 5 block by the earth. Okay, so there we go. 5 comma earth. So on the 5 kilogram block, if I were to ask to draw all the forces, I would definitely include the fact that it's scrunched up against the table, and there is that normal force perpendicular to the surface on the 5 kilogram block by the table. So that's there, and because it's not vertically accelerating, I know those must be equal to each other, but each one of these blocks is connected to a string. So there's got to be some tension on this 9 kilogram block, and so this is on 9. Now it's by the rope, but really it's coming from, that's going to be from object 5 too. I mean, it's the rope is the actual object, but 5 is kind of attached to the other end of it. So that's on 9, coming from what's behind it, from 5. And then on 5, there's also a force of tension going to the right on 5, and that's really coming from what the 9 block is going through that rope. And so because force of tension is force felt the same throughout the rope, and these are actually going to be equal in magnitude due to Newton's third law, but opposite in direction. If I look at the whole table as my system, these force pairs are going to end up canceling with each other. And I look back at this little guy here, I'm going to draw some small tension coming from force of tension of 2 on 5 by 2, and then there's going to be that force of tension over here on 2 by 5. And so you notice I had to draw that smaller. There's going to be less tension in that rope, and those are going to end up being Newton's third law force pairs that, when I look at the system as a whole, I can cancel. They're not gonna have a thing. So if I wanted to draw help minus hinder equals ma, like all at once, I would say the force of gravity on 9 minus the force of tension 9 comma 5 plus the force of tension 5 comma 9 and etc. And I can put all those forces in there. But at the end of the day, the only forces that were left that didn't cancel was the force of gravity on the 9 kilogram block minus the force of gravity on the 2 kilogram block. Those were really the only forces at the end of the day that were helping or hindering this 16 kilograms of mass from accelerating. And so now that I know the force of gravity is just mg, I've got 9 kilograms times 9.8 minus 2 kilograms times 9.8 is equal to 16a. And I'm going to get my acceleration of the entire system as being 4.29 meters per second squared. Okay. Now, if I were doing a free response question, I would probably write out all of these forces and show that they're canceling, and then kind of rewrite this one here. To get to that final help minus hinder is equal to the acceleration. And I would also kind of show that Fg is equal to mg in some way. I would show that step if this were like a free response question. All right, this has been example number 11, and I hope that this has been helpful.